let's start to take a look at some machine instructions. Now, an instruction usually can be divided into something called opcode and something called operands. And this could be done either at the just binary level or assembly language level. Okay, opcode specifies what operation you want. You can think of it as almost like a little function call, right? The name of a function and then followed by parameter list. The parameters are like the operands. Opcode is like the function name. Okay, and now operands or the arguments to an opcode could be accumulator, register, some constant value, value memory, value through a pointer, and all that. And we'll see these. So here is, I think, an almost complete list of opcodes in 8051. I may be missing one or not too many. I mean, this actually is not a long list of opcodes. So there's move, move X, move C, exchange, exchange D, push pop, add C, sub B, multiply, divide, AND, OR, XOR. There's the rotate right, rotate left through carry, rotate right through carry, swap, increment, decrement, clear, set B, complement, and DA. Some of these, I think you can take a look at the instruction set documentation if you are interested. But I'll go over kind of the key ones. No op, which means do nothing. A jump, L jump, A call, L call, return. And then there's a bunch of these jumps. Jump if B bit is set, jump if B is not set, some bit is not set. Jump if carry is set, jump if carry is not set. Jump if 0, jump if not 0, jump. Actually, it should be S jump. And then CJNE, DJNZ. Okay, not that many, but I think after seeing a few examples, you'll know exactly what each one means. Okay, you might say, "Wow, I don't have no idea. Am I gonna have to memorize these?" Eventually, but no. I mean, this is simple enough. I think you'll have no problem memorizing these. So let's take a look. So first, data movement instructions. Now there are a couple of these instructions for just moving data. They have to do with data residing in iData, data residing in code memory, or Xdata, right? Remember, there's three memory spaces, right? So they're roughly divided like this. Okay, so we'll first look at within iData. And remember, iData is this 256 byte space that's very close to the CPU. In fact, the first 32 bytes are mappable to the banks of registers. Okay? So when you see a move instruction, MOV, move, that's mnemonics for moving data to or from iData. Okay. And that means you fetch things from iData into one of the registers or accumulator, or you store data from the CPU, could be accumulator or something, to this iData memory. Sometimes you do 1 bit at a time, but mostly it's 1 byte at a time. And there's also push and pop instructions. Again, these are hardware supported operations that work on iData space. Okay, so you can push an item on a stack, pop, and the hardware maintains the stack pointer. Now, if that's too small for you and you have to use external data for your stack, yes, you can do it, but you have to write code for doing that. If you use push and pop, it increments or decrements the stack pointer for you. Or if you make a function call, it also makes use of this stack. And that's hardware supported. Now, so if you want to use move instruction with the Xdata memory, then you use move X instruction. If you want to use code memory, then you use move C. Move X and move C both require you to specify the address using DPTR, or the 16-bit data pointer. Now move X is two ways. You can write to it, you can read from it, but move C is one way only because it's read only. So you can only read from code memory, you cannot write to code memory, at least not directly. Okay, and you say, well, then how am I supposed to write a bootloader for a little board like this? Well, there's some other ways you do it. You do it through some other implementation specific special function registers, but you don't use move C to write to your own program memory because it's simply not allowed. You can't even find an instruction that lets you move data to code memory. It's not supported by the instruction set because when this was invented, the processor is not supposed to write to its own memory. That's just the way it works. Okay. Now, there's also exchange instruction, so XCH and XCHD. Now, XCH allows you to do a swap between some maybe iData location or register with the accumulator. Okay. So for detail, you can take a look at the instruction reference. Exchange D does only half a byte at a time. Okay, so now move instruction. This is a fundamental operation. And the syntax in general looks like move and then destination source. So think of it as, if you're familiar with C programming, right? Left-hand side gets right-hand side. So that's that order. So left-hand side is the destination, right-hand side is the source. Okay, so you write the right-hand side to the left-hand side, right? Like an assignment statement. And that's the general format for move. But then there are many possible combinations that are allowed. So destination and source, these are again called operands. Destination could be A, B, R0 through R7, DPH, DPL, and a bunch of others. Source can be A, B, R0, R7, or actually a few more. Something called immediates. What's an immediate? Well, if you have taken any assembly language at all, you remember immediate is a constant, okay? And or literal value. So they are usually written with the pound sign in front. So pound sign 12, that specifies the value 12, not address 12, not register 12. Well, there's no register 12, but okay, so that's a quick look. But not all combinations make sense. Some combinations are nonsensical. Okay, so now before I go on, I just want to point out some, you might call idiosyncrasy with Intel assembly syntax. So what I'm about to show you is going to be a bunch of assembly code. Now, assembly language has to follow some syntax. Different assembly languages look somewhat alike, but still there's something specific about each one. And so what I'm showing you here is based on the Intel syntax. And that's what you'll find in the ETSIM, as well as a lot of the documentation. Okay, not everybody follows Intel assembly syntax, but it's good to know. It's not too difficult. There's some idiosyncrasy or something kind of strange, but it just takes a little getting used to. Okay, so the first part is not so strange. If you see pound sign something, well, yes, like pound sign 12, that means 12, and actually 12 in decimal or base 10, right? Now, but you also often need to specify hexadecimal, right, or base 16. Now, you might say, oh, I know C programming, 0x and then something. Yes, some assemblers actually follow that format, but not Intel at that time. This was late 70s, early 80s. Actually, C programming language was just getting popular. But this dated way back before C programming language. And there are different notations for writing hexadecimal. So Intel's way is to put the base after your numeral. So 12 hex is 12H rather than 0x and then the hex number. Okay, so you should get used to this, and because this is going to be everywhere. So so if you see pound sign 12, it's decimal 12. Pound sign 12H, that's hex 12, which is decimal 18. Okay, but one thing though is you can't just put an H and expect it to know how to process it. So if you do pound sign like FF, which is valid hexadecimal, and then put an H afterwards, is that going to work? Well, no. Why not? Because Intel has this rule that if you do pound sign and you want a literal, it better be a digit from 0 to 9. But F or anything like A, B, C, D, E, F, that's not a digit from 0 to 9. So what it's going to do is it thinks, oh, FFH is a name rather than a hexadecimal literal. Okay? And so it's going to see, oh, FFH, that's just like any other variable, foo, or hello, or my variable, right? Something like that. It has no way to tell that that's a hexadecimal. I mean, just because it ends in an H doesn't automatically make it hexadecimal. It can't guess. So the way to do this is in Intel assembly syntax. If you want a literal, hex literal, that does not begin with 0 through 9, you have to insert an extra 0 in there. So to say FF, which is very common, right? 1111111, you actually have to say pound sign 0 and then FF and then H. Because as soon as the assembler sees a 0, it says, oh, I'm expecting a number, and it then can expect to parse the 0 through 9 and then all the hex digits, and then sees the base. Okay. Now, but some of you might wonder, hey, but each hex digit is 4 bits. So 0FF, does that make it 4 times 3 or 12 bits? Actually, no. It knows that this is, it knows the context for what you need. So it still treats it as FF, or 8 bits of 1. Okay. So that's just an idiosyncrasy you should know about.